Poisson for inviting me at my first in-person conference in 2 years. I thought I would speak about some recent stuff that I've been thinking about relating to groupoid representations, certain types of groupoids that are related to flat connections with singularities. And maybe to begin, I'll just start with something kind of classical, which are differential equations with singularities. So these are just ordinary linear differential equations. So here you can think of y as a column vector, and A is a holomorphic n-by-n matrix. We can expand it in power series if we want. And the presence of this z here means that this equation has a singularity at the origin. If you want, you can think of this as a connection. When you write it like this, it's clear that there's a singularity at the origin. So if you kind of wrote the complex plane, you'd have a singularity here. So the solutions to the equations, they kind of, in general, they'll be multi-valued on here, and they could have vanish here or kind of a pole, something like that. And so these have been studied for maybe over 100 years. And I just want to start by talking about some kind of classical story, which is due to Fukuhara, Levelt, and Turretin. So the basic idea is we want to kind of classify these and maybe put them into a simple form where we can solve them. And the basic way to do this is using a gauge transformation. And just from the perspective of ordinary differential equations, you can think of that as kind of doing a coordinate change for the y, where you replace it by g of z times some other indeterminate. And when you do that, it will transform A in the following way. So A of z will go to this. So this will be something familiar. And the goal is to kind of using these gauge transformations, we wanted to reduce the equation so that it has the form like this, where b is constant. And you can kind of think of this as a linearization of the differential equation. So the kind of the classical strategy of doing this is you just do it kind of order by order. So you have this matrix, holomorphic matrix, which has all of these orders in Z, and you only want to keep the order 0, so you just kill off the terms order by order. So, for example, if we were kind of at this point, we killed off everything before level k, then what we can do is just let's try gauge transformation like this. And if we plug this in and kind of only work up to order k, we will change A to terms. And so in order to kind of kill off this term, that means that we need to solve an equation. We have to find a C that makes this all 0. So we need to solve this equation here. So here there's a potential problem, which is that this it might not be invertible. So if you remember, the eigenvalues of the adjoint action of a matrix is the difference of the eigenvalues of this matrix. So if two of the eigenvalues of A0 differ by k, then this thing won't be invertible. And then we're kind of stuck. So this is what's usually known as the phenomenon of resonance, which is kind of the main subtlety in studying these equations. And this kind of blocks the goal of getting to this form. But it's not a huge problem. We can kind of proceed anyways. We can kind of kill off every part of AK except for the part that's in the corresponding eigenspace. So if the corresponding eigenvalues was like lambda I and lambda j, then it would be like a matrix in the like ith row and jth column or something that we would get. So the result is that you can still do this. I mean, except for this one issue, and what you get to is not linearization, but you get a normal form like this. So you can always bring the equation to this form. So here, S is semi-simple, meaning it's diagonalizable. And all of these ni's are nilpotent. And they satisfy if you take the commutator of S with ni, it's I times ni. So that's exactly these resonant terms that we couldn't kill off. Yeah.
Sorry, this implies that there will be only a finite number of them, right?
Yes, yeah, that's a good point. Yeah, this equation here, yeah, it's saying that this is an eigenvector for adjoint action of S with eigenvalue I. There can only be finitely many because that's finite. So this is the kind of the classical result of Turretin. And one way you can interpret it is as a Jordan decomposition. So you can think of this in the following way. So this defines a connection, which you can write like this. So this is kind of a semi-simple connection. So let's call it like that. So say this is the original connection, and we're defining the semi-simple part of it to be this. And then this n of z we can check that in fact this equation here tells you that this is an endomorphism of this semi-simple part. So what we get is kind of a Jordan decomposition for these connections. And in the, I think, 70s or 80s, Lavelle proved that this decomposition is unique.
Sorry, what do you mean by endomorphism of connection?
So if you try to use this to do a gauge transformation, it will just spit this back out.
But wait, for gauge transformation, don't you need something convertible, the exponential of that, or?
That's true. The exponential would also be an automorphism of this.
So are you saying that the exponential of this gauge transformation transforms nabla SS into nabla
nabla SS, from nabla SS to itself.
to itself. Okay.
So in fact, this just kind of works on the holomorphic level. What they did is actually more. They considered the story, but with kind of arbitrary integer k, so irregular singularities, and there everything goes through at the formal level. It's kind of a different story, but you end up still with one of these positions. So it's a very useful result, which has been found. It has lots of applications. One thing that you can do from this point is you can kind of read off all of the invariants of the connection in a straightforward way. So you get, for example, the monodromy. So I mean, like the parallel transport around a loop like that. It's given by just the exponential of 2 pi I s times the exponential of 2 pi I times n, evaluated at 1 if you want. And you also can read off the so-called Levelt filtration. Well, in fact, a refinement that is due to Simpson. So this is a decreasing filtration that encodes the growth rates of the solutions to the equation, and you can just define it in the following way. So it's going to be like a sequence of subspaces of the kind of, if you want, the fiber over this point here, which over here you have maybe a c to the n. So you get a decreasing filtration indexed by real numbers, and the way that you can define it is, say f sub r, you just take the sum of all of the eigenspaces, write it like this. So you look at all of the eigenspaces, and you kind of look at the real part, and you just make sure that it's above a certain real number.
Sorry, on previous formula, I get a little bit confused. Why n of 1? Why not n of any other number?
It could be n of any other number. That would correspond to like a. So I'm doing the parallel transport around the loop starting from 1. You could, of course, go anywhere.
So you're saying they're all in the same conjugacy class? Because the conjugacy class probably cannot change. Or
Exactly, except at the point 0. If you plug in n equals 0, then it will change. Yeah, so it's something I'll get back to actually.
What does it mean at the point 0 to do? Because 0 is the singularity of the connection. So
0 would be the kind of residue.
limit, or
Sorry?
what does it mean parallel transport at the point 0?
Yeah. So what you get at if you just plug this in and you look at what you get at 0, so n of 0 is just n0, right? That actually it commutes with s. So if you looked at exponential of 2 pi I s, exponential of 2 pi I n sub 0, so now you can kind of bring them into the same exponential. And s plus n0, that's actually a0. I should have written that. So you take the residue and you exponentiate it.
But geometrically, it's some limit of the holonomy around, or what?
Yeah, exactly. If you just wait maybe 5 minutes, I'll explain it from another perspective, and it will become obvious. Yeah, so I just wanted to say this is very useful because you can kind of read off these things. And I mean, these are really the only invariants of these connections. You get an equivalence between these kind of Fuchsian ODEs up to gauge. It's equivalent to this data of this filtration and a monodromy. And by the way, the monodromy, it preserves these subspaces. So this is kind of the classic classification theorem, which is due to many people like Deligne and Bolt. Okay, so I just wanted to recall that. And so what I want to talk about is, first of all, I want to re-explain this from the perspective of Lie groupoid representations.
Sorry.
Yes.
So you're saying you can recover from M and the decomposition of Cn, all the components, n0 and 1.
Yeah, exactly.
Okay, that's like some linear algebra exercise which
Yeah, if you think about it, you have the monodromy, so you can recover the connection everywhere except for the origin. And really what you're missing is kind of the growth rates of the solutions as you go to the origin, and that's encoded by this.
So it's not just M of 1, it's all of...
No, it's M of 1 is okay.
M of 1.
Yeah. So what I'm going to do is explain the story again from the perspective of Lie groupoids, and then I want to explain then kind of a generalization in another direction, and then hopefully I want to give a couple of applications of that.
And this F sub R, the little r are real numbers, or?
Yeah, real numbers. It's like the growth rates of the solutions. So there's, let me write the equation again. So there's a groupoid sitting in the background that we can use to study this. And it's very simple. It just comes from the fact that you have an action of C on the affine line. By the way, the affine line, it means C. I'm just using A to distinguish it from the C that's acting. So there's an action which is given just lambda acts on Z. The way that it does it is we take the exponential of lambda and multiply it. And this gives an action groupoid. And basically what we can do is we can convert this equation into an equation on the groupoid. And the way that we can do it is the following. So I'll just write the equation. So it's an equation. It has an initial condition. And here, phi is supposed to be a map from here into GL and C. So notice this equation, so this one has a singularity. This one's perfectly smooth, right? And it's kind of, really, if we think of the groupoid like this, it's really an equation on all the fibers. So there's going to be no monodromy either. So we can just integrate this with the ordinary existence and uniqueness that you know from, I don't know, first year, second year. And so what this gives, when we solve it,
Maybe, but what I find at the moment slightly confusing, right? You had in the differential equation, you had this d over dz on the left-hand side, which encoded your singularity. And now in this new equation, you ignored. We don't know whether it was d over dz, z to the n over dz, right, on the left-hand side. So how this thing doesn't seem to know about it. Is it okay?
It's encoded in the structure of the groupoid.
Okay.
If it was z to the n, you would put there e to the lambda n, the action or something?
It would be more complicated. It's the Stokes groupoid.
Oh, I see.
Marco and Brent and Travis. So,
Okay.
yeah. I guess I could present this in a more kind of highbrow way. I just wanted to give like the most down to earth, just to show it's just take this equation, you convert it to this one, you can integrate it. It determines this map. And this is, you can check it will be a groupoid homomorphism. So it's a representation. And so really, you have kind of an equivalence between these connections and these representations. And this is just an instance of Lee's second theorem for groupoids, which is, I think, first proved by Mackenzie and Chu. So it's just a special instance of that. So we could either study the differential equations, or we could study their corresponding groupoid representations, and kind of depending on which one you choose, you can do different things. So, I want to discuss again now this problem of linearization. So what's the analog? So we need, first of all, the linear approximation. So what is that? So if we take this homomorphism, and you just plug in 0 in the second component, that's now giving you a homomorphism from C to GLN. It's a homomorphism between Lie groups. So these always have a special form, right? It's going to look like e to the lambda b, where b is some matrix. And so what we can do is define a linear approximation of our representation. And the way that this is defined is just using this. So it sends lambda z to just the original phi at 0, e to the lambda b. That's the linear approximation. And so the linearization problem is to find an isomorphism between phi and its linear approximation. So that's the analog of kind of finding a gauge transformation that puts the differential equation into that special form. And it's the same b that I had before, right?
This b is a of 0, no? Or?
Yeah. Yeah, if you want b, a of 0. Okay, so
What does it mean, an isomorphism?
it means, so an isomorphism means like a map from A to GLN that kind of intertwines the two actions. So maybe g of e to the lambda z, phi of lambda z is L phi lambda z, g of z.
Morphism of representation.
Yeah, exactly. Okay, so we've already seen a minute ago that this doesn't work because of the resonance phenomenon, but it's more accurate actually that the obstruction to the linearizability is given by the monodromy. So now we kind of get a slightly different perspective on the monodromy, we can define it in the following way. You can now think of it just as a map from A to GLN. And it's just defined by sending z to phi of 2 pi I z. And this thing, it's kind of clear from the way it's defined now that it varies holomorphically over C. There's no problem at the origin. That was the, I guess, the kind of mysterious thing from the perspective of differential equations, which is kind of obvious from this perspective. And it's not just a holomorphic map. M is actually an automorphism of phi. And and this thing, you can think of it as the abstraction to monodromy. So really, so this is something I showed in a paper I put up on the archive maybe over a year ago. It's that phi can be linearized if and only if M of Z stays in the same conjugacy class. Over all of A1. So again, we have kind of one big orbit. So the conjugacy class definitely won't change here, but it could change at the origin. So I won't go over the proof. One direction is pretty clear, right? If phi is equivalent to its linear approximation, then the monodromy, it's just, you can put it into the form like that, right? So it's just constant. So that definitely doesn't change conjugacy class. The other direction is more involved, and I don't want to explain the proof today, but the kind of the idea is that you kind of convert this representation into an S1 action and then average. So it's kind of using the fact that this groupoid is not so far from C star action on A, which is close to like an S1 action, and you can average over that. And the kind of obstruction to getting into that form is the fact that the monodromy, the conjugacy, it might not be able to be put into a constant form. Okay, but I want to go back to this point. The fact that the monodromy stays in the same conjugacy class on the complement, which means that over the origin, it will still lie in the closure of a conjugacy class. And so, for example, if the conjugacy class was closed, then it would stay constant. It's only the non-closed conjugacy classes actually cause a problem. And so one thing that you learn about conjugacy classes in GLN is that the only ones that are closed are the semi-simple ones. So it's really the kind of the other part of the monodromy, the unipotent part, which is actually kind of obstructing the linearizability. So that's kind of the idea for the Jordan decomposition, that you want to remove that extra part of the monodromy that's causing you a problem. Once you remove it, then you can just linearize. So that's what I want to explain now. So the issue is that we want to remove the unipotent part of the monodromy. And so that means that we want to kind of deform our representation. And the way that you can deform a representation is using groupoid 1 cocycles. So a groupoid 1 cocycle for a representation phi, there's really not much to it. It's just a map like this, such that if you compose it with phi, that this defines a new representation. And you can write that in terms of a cocycle condition for sigma, but I mean, this is really all that it is. So the idea is to kind of encode the unipotent part of the monodromy in a groupoid cocycle, which you can then use to change the representation. So it's actually kind of simple how you do it. So let me just recall the usual Jordan decomposition. So actually we kind of saw earlier the additive one. Any matrix can be written as a sum of semi-simple plus nilpotent. There's like a group version, which is that the monodromy, it's an invertible matrix, we can write it as a product, where S is semi-simple, diagonalizable. U is unipotent, which, by the way, it means that U of Z minus the identity is nilpotent, and the two commute. And the interesting thing, actually, is that when you apply this Jordan decomposition at every point, this thing actually varies holomorphically. So this is holomorphic, and it actually still defines an automorphism of the representation. Another interesting thing about unipotent matrices, U of Z minus identity is nilpotent, and remember the Taylor expansion of the logarithm involves a power series in here. So the logarithm becomes a polynomial, so we can just apply the logarithm, and this is still holomorphic, and it's an endomorphism of phi. And so what we can do to build the cocycle, it's just the following formula. So the theorem then is that sigma is a 1 cocycle, and so phi sub s, which I'm going to define as just sigma times phi, it's a representation. And if you look at the monodromy of this thing, so when you plug in 2 pi I for lambda, right, kind of this term cancels out, the minus goes up, but then the exponential and the log cancel, so you get just U of Z inverse, and that's multiplying M of Z, so this is just the semi-simple part. And I like to write this as kind of an isomorphism of categories. That the representations of this groupoid, it's just the same as some category that I'm calling JC, where the objects are this pair where phi S is a representation with semi-simple monodromy, U is an automorphism to phi S which is unipotent. The map is just you send phi to phi s mu. Okay, so this is kind of the same classical story, but told from this groupoid perspective, and it kind of has the advantage that, so remember, to get the Jordan decomposition, we had to kind of do the classification, the normal form theorem, and then we could read off the Jordan decomposition. But this, it kind of just kind of produces it in a kind of canonical way, and then we can apply kind of this result here to get a linearization. So you can kind of recover all of the usual classification results, and in my opinion, kind of a more natural way that doesn't involve manipulation. Okay, so are there any questions about this?
Simple question. With respect to the original differential equation, once you know this phi and you factorize it, is it clear how to solve it in terms of phi?
Sorry?
So the original unknown was y.
Yeah.
Do you have a formula for y in terms of phi, s, and u, and so on?
Yeah, well, because you can kind of reverse the procedure. You can use the unipotent automorphism to rebuild the full representation. But if you take this part and you linearize it, you put it into a standard form, it will force the automorphism to also be in a simple form. And then you can kind of figure out what are the possibilities. And then you can kind of reconstruct everything. And you'll get the same result that I erased. It's kind of this normal form. Okay, so I want to now move on to the kind of the generalization.
Just one more thing. In this language, the filtration that you have is what?
The way that I like to think about it is, so a filtration, the automorphisms are parabolic or a unipotent group, like the upper triangular matrices are the, and the way that I like to think of it is, first of all, a linear connection. You can look at its automorphism with the linear approximation. It's like a very simple connection, and its automorphism group will be like a group of upper triangular matrices. And then the way that you could think of the filtration is as just a space of possible linearizations, and that will be a torsor for this group of upper triangular matrices. And that torsor is the equivalent data to the filtration. Yeah.
So the equation for linearization that you've just erased.
Yeah.
So it was relating G, phi, and L of phi.
Yeah.
And it looks a little bit like some kind of difference equation on G. Right? Because it relates G of exponential lambda z to G of z. Is there a way of, right, you know, the difference equations, typically you have some parameter q and you relate your unknown function of q times z to your unknown function at z. Something like that. Is there any way of making this theory talking to difference equations?
I've never thought about it in the way that you propose. There is, I guess, you could do kind of a version of this thing for different equations. It won't give exactly the same thing.
Yeah, so maybe it's
Different. Yeah, you're absolutely right. That going from the differential equation to the groupoid representation is exactly the same passage as to go to difference equations. You could look at, for example, discrete subsets of the groupoid and restrict the representation to it, and you would get difference equation. Yeah. Yeah, that's a very interesting.
There are famous difference equations, and it would be interesting to know whether they fit into that form. Do they correspond to some particular groupoids?
Yeah. Maybe I'll move on just for the interest of time. So, yeah, the observation is that this kind of whole thing that I explained, it's not really essential that the groupoid was C action A. I mean, we just needed some specific properties, and that was just like a very simple example. So I want to explain. I couldn't really come up with a good term for the types of groupoid. I called them maybe weighted homogeneous groupoids. And let me just give two examples of kind of a different flavor before I give the general definition. So the first one is, let's take G, a linear algebraic group, and V, a rational representation. So then, of course, we can form the action groupoid. It won't be, in general, sort of simply connected, so I want to take as my groupoid the sort of simply connected version. So I take the universal cover of G, and it acts on V. And so let's look more closely to see what structure this has. So first of all, we have the Levy decomposition of G, which says that G can be written as a semi-direct product of U and R, where U is a unipotent group. You can think it's like a subgroup of the upper triangular matrices. And R is a reductive group. And up to a finite cover, which doesn't matter because we're going to take the universal cover anyways, R can be written as a product of a torus, and S, which is a simply connected semi-simple group. And so this groupoid, G, which can be given like this. And this, it receives some maps. So first of all, C to the K is a subgroup of this whole thing. It's not normal, but it's a subgroup. And it acts on V. And so we have kind of including into G this groupoid. And also, we can, because U is normal, we can kind of project off this part and then also project the C to the K. So we have a projection map like this, and the composition is like the usual projection. And sitting inside of here is Z to the K times V. And this it lies purely in the isotropy. It doesn't act on V. And not only that, so even though C to the K, it did not commute with everything else, because we originally started from C star, and then we took the universal cover, this lattice Z to the K is going to act trivially. So this is actually central. So it's a subgroup which is central and purely isotropy. Okay, so that's example 1. Example 2, which is of a different kind of flavor. So I want to let X be C2. And inside of here, I'm going to take a submanifold, D, which is the vanishing locus of a function. And this function is x squared minus y cubed. So this is, it's kind of a curve with a cusp singularity at the origin. And so, for example, just a little bit about this space. If you look at the complement of D, this is homotopic to the complement of trefoil. Okay, so I want to look at, well, I'll first describe the algebroid. So the algebroid is Tx minus log d. So this is the algebroid whose sections are the vector fields on X that are tangent to D. It's generated by two vector fields, E and V. So E is a generator of a C star action. It's not going to be the standard one. We're going to take the one that has weight 3 in X and weight 2 in Y, so that F is now homogeneous of degree 6. So and V, it has the following funny formula. And this is a vector field that just annihilates F. Basically just cooked up to do that. And if you take the Lie bracket of these two things, you just get V. So you can just think of this then, that this Lie algebroid is, it's an action algebroid for the action of this G, which is the unique non-abelian two-dimensional Lie algebra. And, okay, so this thing, it has an integration, which is called the twisted fundamental groupoid. You might think that it's going to be an action groupoid, but it's not, because V is not complete, so it's not an action groupoid. Nevertheless, we get mapping into here an action groupoid of this form. This is the groupoid that's generated by the action of E. And this, it projects to C. By basically, on the infinitesimal level, you kind of project the G, and the subalgebra generated by E, you can project on, well, you project out V, and you get to E. So you get, again, this sequence of maps, so it's just like before. And the composition is the projection, and sitting inside of here, you have Z times X, and it satisfies the same properties. It's isotropy, and it's central. Okay, so the general kind of definition of these weighted homogeneous groupoids comes from the following data. So first of all, you need an action of C star to the K on some manifold X. 2 is that you want a Lie groupoid over X. And then third, you want kind of a factorization. You want a map. So here, this is the source simply connected action groupoid corresponding to this thing. It needs to map into G, and then G has to project to C to the K in such a way that the composition is just the projection. And so we get, again, inside of here, a Z to the K. And it's purely in the isotropy. And we just need to make a requirement.
This covers the action downstairs of the C star to the K?
Yeah, exactly. This one does. Yeah, so that because it's coming from a C star to the K, this, when we go to here, the Z to the K acts trivially. And we need to require that Z to the K is central. This is actually not so difficult to achieve. For example, it's going to be true if the anchor map of the algebroid of G is kind of generically injective. Then this is automatically going to be true. And then we need another thing, which is kind of a technical requirement, which is that we need what I'll call a single S equivalence class. It just means that you can define kind of the orbits of G that gives you an equivalence relation. You can define kind of a weaker, or well, you can define an equivalence relation where you say that 2 points are the same if the closures of their orbits meet. And under this equivalence relation, you want there to be a single orbit. And that's also not difficult to achieve. It will be true, for example, if there's kind of a dense orbit, or, for example, if, like in this case here, C star to the K is acting on V, we'd want maybe one of the factors of C star to have only positive weights, so that 0 is in the closure of all orbits.
I'm sorry, the map pi, what is, it's just, does it do anything relative to the groupoid structure?
Well, it's a groupoid homomorphism.
Okay.
Yeah, these are all groupoid homomorphisms. Yeah.
2 minutes.
Okay, so maybe I'll need like 5 minutes, but I'll skip some stuff. So, maybe let's just say, so for these things, these are kind of exactly the types of things that you can use to define a Jordan decomposition. Which is, okay, so the way that you can do it is as follows. So suppose you have a representation like this. Then by restricting to this Z to the K subgroupoid, you get a monodromy. And you're going to do the same type of game where you take M and you factor in a semi-simple plus unipotent. And then you take the unipotent part and you take the logarithm. And then what you want to do is kind of extend this to a map from C to the K. So that will define kind of a map L from C to the K times X into GLN, just by kind of extending this. And then this is basically just what you need to define the Jordan decomposition. So you can find the cocycle now in the following way. So you want to map from G to GLN. So first you project to CR times X. And the way that you do that is that you apply pi to go from G to here, and you apply the target. Then what you do is you apply minus L, right? So that will go to GLN, and then you exponentiate. And that will go into GLN. And then the theorem then is that, so this composition is that sigma defines a groupoid 1 cocycle, and so phi sub s, which is sigma phi, has a semi-simple monodromy. So the kind of the same result holds, and then you can do the same thing as for the C action groupoid, where you can kind of try to now linearize a portion of the representation to kind of obtain normal form. So I guess I'm out of time, but I wanted to discuss for example, in this example, you can get some nice normal forms for what the flat connections with singularities along D looks like. And then you can also do kind of funny things like if you have a connection that's defined on the complement of this singular point, you can use this decomposition to kind of extend, to show that you can extend it uniquely kind of to D. And kind of combining this with a result of Deligne for kind of extending connections, you can show that the representations of the fundamental group of the complement of D, they all arise from these logarithmic connections. But I'll end here. Sorry for going over time.
All right, questions?
Yeah, I have a question. Is there any similar results on the genus 1 or genus 2? I mean the differential equations on this genus 1 or genus 2 surface?
You mean with singularities? Like?
Yeah, some similar results.
Yeah, so if you have like a Riemann surface and you have some points, and you can study flat connections that have singularities along these points, and you can study these from a groupoid perspective. I wrote about this in the paper I put up like a year or two ago. Yeah.
And if two of those points coincide?
Like higher order. Well, there's still a groupoid whose representations correspond to those connections. It is the one from the Stokes groupoid paper of Marco, Travis, and Brent. So there's kind of part of the story, but so for example, the Jordan decomposition doesn't work for those ones because it only holds on a formal level. So there's other things that you'd have to do. Yeah, there should be some kind of story for that as well.
If I understand correctly, your result gives a classification of the representations of those groupoids, right?
Yeah.
G?
Yeah.
But can you? It's like the source fibers of G are copies of CK.
Here?
Yeah.
No, I don't think so. Because it's
Maybe the generic source fiber or something.
no, wait, because for example, what was the example? Oh, I erased it. It was the action. The group was. Source fiber. It was like this group, this action groupoid. So the source fibers were this thing here. And similarly, in this case, the source fibers of the groupoid will be like. I mean, it will depend on what orbit you're on, but if you're up over here, it will be the universal cover of this thing, which is like. I mean, it's like the universal cover of this face. On the top here.
If there are no more questions, let's thank Francis again.